This is my solution for the problem that we did Tuesday, week 7. And we were starting to talk about magnetism. And so the question was, if you have some loop, find the magnetic field at the center of a loop of current. And this is sort of the side view. But let me draw the top view. And so this is the top view, and we want to know in the middle. And let's say the current is going in the counterclockwise direction, and the loop has some radius r. So the first thing we want to do is figure out what the direction is. And there's two ways to do that. Well, probably lots of ways to do that, actually. But what you want to do is start with the definition of what magnetic field means. And a little bit of magnetic field is mu naught over 4 pi times the current times a little bit of that current's path along the direction that the current is flowing cross r hat all over r squared. And we said that this part, this cross r hat, just means that it is perpendicular to the current and perpendicular to the distance to the point in question. So that's all it really does. And so in the case of my top view here, the current's in the plane of the page, and so is the distance from the current to the point in question. So that means that it has to be perpendicular to those two. So my only choices are into the page or out of the page. And one quick way to figure this out, as we talked about, is that if you put your thumb, so if you put your thumb, here's my hand, this is my right hand, and the thumb in the direction of the current, your fingers, these are my fingers, how many fingers do I have? I have 4 fingers, curl in the direction of the magnetic field. So they point in the direction of the B field. And so at the top of this loop, if I put my thumb in that direction, in the middle of the loop, it comes out of the page. If I put my fingers in the direction of the current at the bottom of the loop, so they go to the right, again my fingers point out of the page. Now it's true that they point into the page outside of that loop, but that's not what we were asked. So the picture that goes with this problem shows that it really doesn't matter where you're trying to find the field. Anyway, okay, so now we can proceed. And in fact, what looks like an integral really isn't, because the path that the loop is taking is the same distance from the point that we're thinking of. And so I could write this as I say r d theta, which would be at some distance r a little bit of current, and then integrate over r squared. But really, why would I even bother? Because once I do this, I'm just going to get I times 2 pi r, the circumference of the circle. And that's really what I encourage you to do when you can. So divided by r squared, and we have mu naught over 4 pi, and I think that's it. That's the whole thing. And so the pi's cancel, and the 2 cancels with one of the 2's, that's the 4, and the r, and what we get is mu naught times I divided by 2r. And the point here is that you could take these little pieces and integrate them together, but the symmetry of this problem makes this quite a bit easier. Now remember, if we were to find it at some place other than the center of the circle, we'd get a different answer. But this is probably the easiest example we can do of what's called the Biot-Savart law.